So this is Geometry Semester 1. It's the unit called Rigid Motions, number 6, and it's the lesson called Stretching Practice, lesson 6. All right, it's on creatormath.com under the Geometry tab. You might have to Google creatormath.weebly.com to find the site. The instructions are copy the following problems into your composition book on the correct pages according to the table of contents with the notes for those pages from creatormath.com. So to help you try to navigate that, here's the website name, creatormath.weebly.com. That's what you may have to Google to find it. The home page should look like this when you get there. If you need to know anything about your composition book and taking notes, then go scroll down until you see the words composition book and follow all the videos, the directions, the turn-in dates, etc. under that. And you should have a 90 to 100% on your comp book. I hope that's a great booster for you. We're going to go to the Geometry tab, which is where all the notes, the videos, the practice sets, the vocabulary, everything is under the tab for the class you're in this case, Geometry. So here's the PDF for all the vocabulary for the entire year. It is searchable. Make sure you save it to your device. If you don't know how to search it, just Google how to search a PDF with whatever device you're using, and it will give you instructions. We're going to scroll down to the semester that this unit and lesson are coming from. And we're going to see the table of contents. This should have been copied onto pages 2 through 6 of your composition book. If not, watch the videos on how to number your pages and watch the videos on how to fill out your composition book, and stop what you're doing now and put in this table of contents. We're going to scroll down to the unit called Rigid Motions. Here it is, and the 6th lesson. So there are 6 lessons here. Each is here. There's notes and problem sets for each. So in your comp book, this is called stretching, and it goes on these pages in your composition book. Please check the actual table of contents at the time you're viewing this video, because by the time you watch this, these actual pages probably will have changed. So here are the notes. Fair warning, it does take me a couple times some time to open this. So let's see if it opens today. It opened all right. You should be able to expand it on your screen, and you're going to take these and start to write this into your comp book. So we're going to use desmos.com, and on your iPhone, iPad or phone, it says on the notes on the board. That's cute. It's whatever device you're on, you guys. You're going to go to desmos.com. We're going to look up trig functions, sin x, and we're going to type those in and have a graph for us. And then we're going to start to play with those functions and say 2 times sin x, and we're going to see how it stretches the graph. So these notes you're going to put into your comp book, you're going to label these, and then we're going to go graph them and show you what we mean. Here is the graph of a tangent function. So we'll look at that one and talk about the center of dilation, because as we stretch these, there is a center of that dilation. Right now, just to cover the topic of rigid motion versus dilation and stretching. Dilation and stretching are technically not rigid motions. Rigid motions are where the shape stays fixed. This is where the shape is changing in terms of either expanding or contracting. So technically speaking, these are not rigid motions, and a little bit of an apology for putting them under this unit. But at the same time, it's kind of the best place to go ahead and put them, so they reside under this unit name. These lessons do on dilation and on stretching here. Okay, so we're going to use desmos.com because we don't know these functions yet. We're going to play with something we've never experimented with before. We're going to type those into Desmos. And what is the idea of dilation? Stretching or shrinking. Stretch, to extend a shape. Dilation in a single direction by a scale factor. So now we're talking about a single direction, either vertical, like if we stretched it this way, and just think of your screen, right? Now your screen dilates in all directions, but imagine we could change just one dimension. The lettering would get quite distorted, right? So maybe you can think about that as we go through this. Shrink means to reduce a shape, dilation in a single direction by a scale factor, all right? There's some problems, I think, here for you to put, and vocabulary for you to put into your composition book. Just keep in mind horizontal is left to right, and vertical is up and down. Right? Scale factor is the amount we either multiply the expansion by or divide the expansion by. So if we multiplied something by a 1/2, that's technically dividing it by 2. All right, just a little bit of reminders. Those all go in your comp book. Now let's look at the problems we've got for this set and see what we can do. So what's the pre-image in relation to stretching? So this is going to give us some review, you guys. Pre-image is the image we start with before we stretch it. Okay, so this is the image before it is stretched. What is the image in relation? What is the image in relation to stretching? The image is after it's stretched, right? So we're going to start with an image. That's the pre-image. Pre being before something happens to it, right? In this case, we're stretching it. And image being what happens after it's been stretched, right? Pre-image and image. That's the vocabulary you'll need to have as for understanding where we are in the process of did we stretch it yet or not. How is the following notation spoken? So you'll see this notation a lot when we deal with rigid motions and non-rigid motions like dilations and stretching. We'll have something labeled A, and then we'll have A with an apostrophe or a tick mark. That's called A prime. It is an apostrophe, but we don't call it A apostrophe. We call it A prime, all right? Just some notes on. So if you had a triangle here and it was A, B, C, right? And now we had another, say we dilated it, and now it was A prime, B prime, C prime. Typically this is the pre-image. Typically this is the image, which is after it's been modified, all right? Okay. With that, let's get into what were the meat of the lesson here. Given the following graph, and remember these are the problem sets, you're going to need those notes in your comp book to give you the background to it. If the red graph is sine x and the blue graph is 2 sine x, then the graph has been, and here are our answer choices: stretched vertically, stretched horizontally, shrunk vertically, shrunk horizontally. All right, 4 choices. So some problems with this question, with me going over it like this. You're going to be looking at this on your screen. You're going to be able to see the red graph, right? You can't. So let's try to clean up that issue by going straight to desmos.com. Can I do that? Let's see if I can do that. Here we go. So let's go to desmos.com. And let's try to mimic what they've got. They've got 2 functions here. They've got sine x and 2 sine x. So here's how you type this in to Desmos. We're going to say y equals. We need that for the graph to understand there's a y-axis, all right? So now, I don't see any sine x, right? Let's do functions. There we go. I forgot for a second. So look at this. All kinds of functions you've probably never seen before. Maybe you have because we've been through trig in some classes. Maybe not by this time, the time you're viewing this. But sine, cosine, tangent, cosecant, secant, cotangent. Those are going to be the main. These are inverse functions. Sine to the -1 is the arc sine or inverse sine. Cosine to the -1 is inverse or arc of cosine, inverse of arc of tan, inverse and arc of cosecant, etc. We'll explain more. Hyperbolic functions you won't use till algebra 2. We won't cover those in geometry. This is sort of a little bit stretching beyond and a covering of the standards, you know, for you to sort of see where we're headed. So let's do sine. And let's put an x in. All right, there's our wave, you guys. Sine x makes a wave. And here's one complete cycle. We're starting here. We're going up the curve. There's the top, called a maximum. We're coming down the curve, crossing the x-axis again to here, called a minimum. And then we're repeating, if you look, this sine wave keeps going up and down, up and down, up and down, and it goes forever, actually. So let's see what happens. Let's do another graph. Let's say y equals... And I expect you to repeat this on your Desmos, on your device, all right? For you to just watch me do it is one thing, but you need to play with it yourself to get this experience. So put in 2 times function sine x. And I guess I could close the parentheses so it looks better to me. So notice now, the red is the original. Notice what has happened. It's still crossing the x-axis at these points. So it's not being stretched horizontally. But notice how high it comes. The graph is coming almost twice, well, not almost, but twice as high and twice as low. It came here 1 unit down. Now it's going 2 units down. So we can actually find out where these points are. Pi over 2. Look at that, comma 2. We're not going to get into that. We're simply going to deal with, has this graph been stretched horizontally or vertically? That's all we're going to do. All right, so we're going to play with Desmos at this level in geometry, we're just trying to get a expansion into the idea of, is this being stretched horizontally or vertically? In this case, it's being stretched vertically, right? So we're going to do stretch vertically. That's our answer choice here. And so that means that, you know, if the red graph is signed, this must have been red, just like in our actual example here. The red was the first graph we did of sine, and the blue was the second of 2 sine. All right, and 2 sine stretched it vertically. All right, given the following graph, if the red graph is sine x, let's go ahead and do this again. Okay, so now they're graphing sine x, and look what they're graphing, 1/2 sine x. Can we predict what's going to happen to the graph? On the last example, we multiplied the sine x by 2, and it stretched it twice as much vertically. What if we now multiply it by 1/2, or, in other words, divide it by 2? Could we expect the opposite? So it's a little hard to see which is the original here, but this is the original here, right? And let's go ahead and do it. Let's take our example here. Let's stick with sine x, and now we're going to turn this into a fraction of 1/2. Let's get rid of this and say 1 divided by 2. Sometimes students say, how do I get a fraction in there? Just say divided by. So red is the original, and blue is the new. What's being happened? It's being shrunk vertically. In fact, cut in half the vertical distance here that it goes up to its maximum and its minimum, right? And just think of a maximum as high as the graph goes and a minimum as low as the graph goes, right? And then we'll get into local max and min and global max and min later. This is just a rough introduction to the idea and to let you play with Desmos and experience what this means to stretch and to see patterns, right? So 1/2 here actually cut this in half. We went from here down to here, right? So it shrunk vertically is the answer choice they gave us. All right. Given the following, if the red is the sine x, so sine x keeps being our base, now we're going to put the 2 in front of the x. So remember last time we put the 2 in front of the sine and it stretched it vertically. What happens if we put it in front of the x? Let's try it out. So we're going to take out this 1/2 here. Let's get rid of this. And let's put the 2 in front of the x, 2 times x. Ha! So here's the red coming this way. Notice that now this graph has been, whoops, here you go, let me make it a little bit better for you. So the red is the original. The blue is being shrunk horizontally. It's being squished together or scrunched up. So now we have the same height. Sorry about that, you guys. So now we got the same height, right? Here it is up, this is same height here, but it's been shrunk, it's been squished down this way horizontally, right? So this has been shrunk horizontally by multiplying something in front of the x. So what do we have here? We're just going to say shrunk horizontally, right? And can you start to think about what they're going to ask us next? Don't you think they might put a 1/2 in front of the x? And if this shrunk it horizontally, dividing that x by 2 and then the sign operating on it, would you imagine that it would be expanding or making it larger horizontally? Okay, let's see if they ask us that. And I believe my prediction is correct. So here we go. They're asking, giving us the original sign, and now they're putting 0.5x. 0.5 is the same as 1/2, right? So 1/2 times the x. Then the graph has been, we're going to say, stretched horizontally, right? Let's go ahead and just check it. Use our Desmos to do it. Let's put a 0.5 right there, 0.5x, and there it goes. So we hit our maximum here. Now it's been stretched all the way over to here where the maximum is hit. This curve has been stretched out horizontally, right? So complete introduction, but I hope that helps. You're going to definitely match up the title to this practice set with this video, okay? Geometry Semester 1. It's the unit called Rigid Motions number 6. And it's the lesson number 6, stretching practice, and it's on creatormath.com under the geometry tab, and hope this helps.